Oh, yeah.
So we're ready to resume. Hello, hello. So we're ready to resume. All right. Okay. So our next speaker is Vidya Muthukumar from Georgia Tech, and she'll tell us all about does the training plus test loss function matter in the ultra-high-dimensional regime, very much in scope for this conference. Vidya, take it away.
Thanks to the organizers for the kind invitation and for putting together such a great program. So this talk is going to be somewhat rethinking our assumptions and understanding about how we think about loss functions, both at training time and test time. It's going to focus on the ultra-high-dimensional regime, which I will make more precise as we go along. Before getting into details, I want to acknowledge my wonderful collaborators, starting with my student, Kove Lai, and my collaborators from some of the older work I'll mention today, Daniel Su and Jisoo. So the starting point for this work is a set of intriguing empirical observations that have been made in large-scale deep learning. I'll start with the observations for in distribution error, which is just a standard notion of generalization error where the training data and the test data are identically distributed. All the benchmarks here are ML-oriented, so they're all classification or 0-1 loss. And the very high-level conclusion from the set of results presented by Hui and Belkin a few years ago was the somewhat provocative claim that training with a squared loss, which is a non-standard loss for classification, seems to yield very similar outcomes to what we get from the cross-entropy loss. And to dig into this a little more, the top panel of figures plots the test accuracy as a function of the number of training epochs on benchmarks across NLP and speech as well as imaging, so many different domains. The blue curves represent what you see with the cross-entropy loss, and the red curves represent the squared loss. And you see that these curves almost overlap with each other, particularly towards the end of training. The bottom table, on the other hand, compares the accuracy for various architectures on common vision benchmarks of like MNIST, CFAR, ImageNet, etc. And again, just if you glance at the numbers, you see that the numbers are very similar for the square loss and the cross-entropy loss. And this was seen as surprising because we tend to use the cross-entropy loss, which is a generalization of the logistic loss for classification, and the squared loss is less common. Nevertheless, it seems to be doing pretty well. The next observation is that we can actually conversely see pretty different behavior for different choices of loss in the case of out-of-distribution learning, where by that I just mean that the test distribution can deviate a fair bit from the training distribution. Common examples where this happens is where we have different groups of data or different mixtures, and some of the mixtures are underrepresented in the training data, but overrepresented in the test data. One set of nice results here by Kinney et al., 2021, compared importance weighting, which is simply like you have per example losses and you upweight the examples that are maybe underrepresented in some sense, and saw that there were subtle effects that arise as a consequence of how you apply the importance weight. So I've written a little bit of math here. A common way of doing this would be putting the weight outside the loss function, so just having like your log loss and then having the importance weight outside. But there are also these variants that have been developed in the literature to bring in the weights kind of inside the arguments of the loss function, and that corresponds to these different acronyms, LA, CDT, VS. And what the table here shows is that all of these variants actually have pretty different effects on the test accuracy, and something called the VS loss turns out to be the most effective. So we start to see differences. And actually one thing that I've not mentioned here but on the slide but is important to note is the standard notion of importance weighting, where you just take the weight and multiply it by the loss, turns out to not be that effective in these high-dimensional settings. And to maybe make that more clear, another set of experiments was done by this paper, Wang et al., where they took the standard notion of importance weighting and compared the standard cross-entropy loss with a kind of polynomially tailed variant of a loss function where the loss decays polynomially as a function of this margin argument. And they actually saw that importance weighting is not very effective in the case of cross-entropy loss, but is more effective on these polynomially tailed losses. So a bunch of observations that were made here that at a high level showed that different loss functions and particularly different variance and importance weighting can yield pretty different types of performance that we do not really understand even in simple linear models. So before I get into the settings I'm going to describe today, I want to start with a little bit of historical context. How do we think of loss functions traditionally? So the traditional statistical perspective has been that we should think of our loss function as the negative log likelihood to connect it explicitly to the maximum likelihood estimator. So it's like fixed design in the covariates, and you have some probability model for your labels, and you design your loss function in this way. And common canonical examples you learn about in an intro to ML class would be, for example, the squared loss under additive Gaussian noise, or the logistic loss under the binary logistic model. So these are very classical examples. There's also formal theory that exists in statistics to explain why this is a good idea. Not going to get into all the details here, but essentially there's a sense in which you can show that the MLE, or equivalently the minimizer of the negative log likelihood loss, would achieve a minimal variance unbiased estimator, and this connects to notions of Fisher information. There's a kind of parallel and slightly more recent perspective that appeared in machine learning theory, which was more concerned with classification and minimizing the 0-1 loss. Here the perspective was that the test loss is 0-1. This is what we want to minimize. This is a nightmare to train on because it is a discontinuous objective. It is not something we want to do. So the idea was to design a good convex surrogate that is amenable to computation at training time, but also does well at test time. And there's a lot of beautiful work on this that appeared in the 90s and 2000s. A canonical result in this space, which was this paper by Bartlett, Jordan, and McAuliffe, essentially said that if you measure your test error according to risk according to some convex loss function given by phi, and if this converges to some nice quantity, you can think of this as 0, but it can also be something else, translates into results on the 0-1 test error. So if we think of the R star quantities on the right-hand side as 0 for thinking of consistency, what this would say is if you get consistency under the loss function phi, you also get consistency for the 0-1 loss. And what this implies indirectly is that the test risk under different phis would be similar. You get consistency under all of these loss functions. And then if you assume empirical process theory, if you're in that domain where things kind of work out in that sense, the training risk would be similar to the test risk, and you would get the similarity in training loss functions for free. So this is how we've traditionally thought of loss functions in one of these two ways. Both of these lines of work require your data to be either fixed in the case of the asymptotic normality theory, or to be sufficiently low dimensional. So none of this is prescriptive for the high dimensional regimes in which models like neural networks operate. And this is where some of our work comes in. I'm not going to say anything about neural networks today, at least not in a very precise sense. But I will focus on ultra-high dimensional linear models. The first part of the talk will characterize the impact of these various loss functions, both oriented towards in-distribution error and out-of-distribution error on the eventual solution. And here I'll present some structural results that do not require assumptions on the output models. I'm only going to be making assumptions on covariates. So I'm going to try to get fairly general structural results. And the second part, we'll start to specialize a little more in terms of signal models and output models, and I'll give you a glimpse into error analysis. Most of the technical content is going to be for the first part of the talk, but I'll give you an overview of results for the second part. Before I get into details, I want to acknowledge some, I think, related and complementary work that also has, I think, some very nice insights about the impact of loss. The first one is this nice paper by Kinney and Trampolidis from 2020. And they looked at linear models with d proportional to n and got some nice precise asymptotic analysis using the convex Gaussian min-max theorem. And they actually found some conclusions that are, we're going to see in more precise senses as we go later on in our talk, which is that as you over-parameterize more, the square and logistic loss seem to be kind of similar. Another nice, I think, toolkit was proposed by this work by Loreto et al., where they used the AMP and again operated in this proportional regime. And they got this state evolution, which is, I think, fairly complicated, but in principle could be used to derive some comparisons between different loss functions. And finally, there was work more in the statistical learning theory side in the spirit of getting upper bounds. And this kind of tries to reconcile our setting of over-parameterized models with some of these surrogate loss style theories. And they derive bounds very similar to the benign overfitting bounds you see for linear regression. As we're going to see in some sense later on, we are able to get slightly stronger bounds in some of this work, but this work is also more general. One high-level difference, other than the fact that many of these operate in the proportional regime and we're not going to operate in the proportional regime, that I want to mention, is that all of these works give you end-to-end error analysis. They assume a signal model, and they don't provide like structural results. And we kind of try to get at structural results. Again, all of this will become more precise as I go along. Okay, so what is our formal setting? So we're going to consider a binary classification data set. By that, I mean that the covariates are d-dimensional and real valued, but the labels will take on only one of two values, that is +1 or -1. This could also be 0, 1. I'm just choosing +1 or -1 for convenience. I'm going to center the covariates, and I'm going to denote by sigma the covariance matrix. For the end-to-end results I will state in this talk, particularly for error analysis, we will assume either Gaussian design or that the coordinates of x are independent and sub-Gaussian with some constant. In that case, sigma would be diagonal. However, many of our results could potentially be relaxed, and I'll talk more about that at the end. Okay, so I've said ultra-high dimensional regime 3 or 4 times. What do I mean by ultra-high dimensional regime? I simply mean that D will grow with N at a super linear rate. And this is, of course, different from the regime that many of you study, where D and N grow together at some constant rate. And in this regime, what we expect is that the data set is going to be linearly separable, almost surely for continuous ensembles like Gaussian, but even for discrete ensembles, linearly separable with high probability for any choice of labels. So it's possible to interpolate even random data in this regime. Okay, so our focus in this talk is going to be on studying the impact of loss function. So what do we mean by that? I'm going to study the outcome of gradient descent for a general quote-unquote loss function. So script L here denotes the empirical risk, where I'm just summing over all of the training examples, and then I have small l of minus yi xi transpose theta. So these are like losses that are very classification oriented. They're based on the training data margin, that is yi times xi transpose theta. Remember that when you want to separate data, you want these quantities to be pretty large. I've just put a minus sign in the argument as a convention. And what this means is, well, the loss would become smaller if yi times xi transpose theta becomes larger. So my assumptions on L are going to be pretty minimal. I'll assume that the loss is convex. I'll assume that it's twice differentiable. This turns out to be needed for some of the analysis techniques. Because I have a negative sign here, I'm going to also assume the loss function is increasing, and it attains its minimum at minus infinity. So minus infinity just means that each of these is going to go to infinity. So because the loss is driven to 0 at minus infinity, I'm going to study the unit normalized outcome of gradient descent, and this is standard in the literature when considering these types of loss functions. But these assumptions are pretty mild, and they capture many common examples in the literature, the exponential loss, the logistic loss, and others, and also this kind of variant called a polynomial loss that I already presented a few experimental results about. And as I just said, the loss is driven to 0 at infinity. Note that I've not done any explicit regularization, so this is like an unregularized empirical risk. Something very important about this setting is that there are infinitely many minimizers, so any discussion about comparing the loss function has to bring in a choice of optimization algorithm. So we need to understand which minimizer we are converging to. So this is where implicit bias, the so-called implicit bias theory comes in. I'm not assuming that people know about this. I'm going to give a very brief introduction. But the basic high-level idea in implicit bias asks, if we fix a loss function and we fix an optimization algorithm, can we understand which of these global minimizers the algorithm is going to converge to? For this talk, I'm going to fix the optimization algorithm to be gradient descent. And I'm first going to review some work that gets at this question. All of the work here is basically worst-case optimization theory. There are no assumptions made whatsoever on the data, other than maybe the fact that the data is linearly separable and appropriately normalized. Okay, so perhaps the most well-known work in this space concerns what are called exponentially tailed losses. This includes exponential loss, logistic loss, and some others. And here what is shown is that the solution of gradient descent converges in direction, that is the unit normalized solution will converge to a very classical object, which is simply the max margin SVM, where margin is defined with respect to the L2 norm. And all the solution does is you can write this explicitly as a convex program. It minimizes the L2 norm, subject to this constraint of attaining a margin which is at least 1. Remember, we want yi times xi transpose theta to be not only greater than 0, but as large as possible. And this is a worst case characterization. This holds for literally any data, not just random data. We can then bring in the squared loss, which is the other loss function that I introduced at the beginning of this talk. And in some sense, there's not even a formal paper characterizing the implicit bias. There's actually a 3-line proof, I think, by Francis Bach that on his blog that's really nice. But here what you can show is if you initialize your model at 0, you would converge to the minimum L2 norm interpolation, which is again a minimum 2 norm objective. But now the constraint becomes a perfect fitting constraint where xi transpose theta needs to be exactly equal to the labels. This is a bit strange in the context of classification, but as we're going to see, it turns out not to be too bad an idea. And finally, when we think about general convex losses, a lot less is known, especially in a worst case sense, and in particular, things become much more complicated. And the only real worst case characterizations here appear due to nice work by Ziwei Ji and Matusz Telgarsky. And they had to work quite hard to get these results as well. And the only sense of convergence we have here is a sense in which gradient descent is shown to be equivalent to some type of regularization path, where you look at the minimizer of the empirical list subject to some constraint on the L2 norm. So this is already, as you can see, a bit more opaque than the other two characterizations that we have over here. All this is really telling us is that gradient descent is connected to the L2 norm in a certain sense. It's not telling us a whole lot more. We certainly don't have an explicit convex program here. What we only have is like a limiting sequence of convex programs. So it's quite difficult to understand. OK, so where our work comes in is we wanted to understand how these different solutions relate. Interestingly, in low dimensional settings where like maybe the data is separable, but D could be less than N, there are stylized examples in which all of these solutions can look quite different. So we wanted to understand what happens in very high dimensions. I'll mention some of the older work that I did on this topic, which was joint with Daniel Su and Ji Su, that sets the stage for some of the things I'm going to say later. So we started by, I would say, trying to compare the solutions obtained by the exponentially tailed loss, that is the SVN, and the squared loss, that is the case of interpolation. And in some sense, this whole research program started in some sense by accident, because our initial motivation was to sharply analyze the SVM. And this is more challenging to do because the SVM does not have a closed form expression, and there are some other reasons it becomes difficult. So we ran this very, I would say, toy experiment where we considered like linear classification on Fourier features. So here it's kind of like polynomial regression, but instead of polynomials, you're using like Fourier features. And here your number of linear model dimensions is just the number of frequencies. So we came up with this Fourier featureization. We considered like arbitrary training data, 32 examples and 1,000 frequencies. And what was nice about this is because it's a featureization on one-dimensional data, you can get your linear model coefficients in terms of the Fourier frequencies. And this is a one-dimensional function representation, and you can actually plot these functions and compare them with each other. And what we found was actually that the minimum norm interpolation, which is what you get from the squared loss, and the SVN turned out to exactly coincide. And we ran a bunch of experiments of this type, and we saw this exact coincidence pretty much all the time. So this was kind of surprising, and we thought, OK, if we're seeing this many times, this must not be an accident, and let's try to prove this result. And we were ultimately able to show that provided the linear model data dimension is sufficiently large, in this ultra-high dimensional sense, the solutions do in fact coincide with very high probability. And here the high probability is only over the covariates. I've made no assumptions whatsoever on the label. So it's like a random covariate result in some sense. To be more precise about the high dimensional conditions that we needed, we defined two common notions of effective dimension. Both of these reduce exactly to the dimension of the model in the case of isotropic covariance. More generally, D2 corresponds to the trace of the covariance matrix squared divided by the Frobenius norm of the matrix squared. And D infinity corresponds to the trace of sigma divided by sigma operator norm. And if you stare at these for a few seconds, if sigma is the identity, then both of these are just going to reduce to D, which is the dimension of the linear model. More generally, your covariance needs to be sufficiently effectively high dimensional. We also have this log factor here. This actually, all of this turns out to be tight. You can actually show that if you do not have these conditions, then this phenomenon will not happen. So at a higher level, this result showed that there's an exact equivalence between the implicit bias of the exponentially tailed loss and the squared loss with high probability in this very high dimensional setting. I did have a proof slide. I think I'm mostly going to skip all the details here. The very high level thing, I timed this before coming here, and I probably won't have time to do all of this. One thing I will mention is that at a very high level is that our starting point was to work with the explicit characterization of the SVM program and kind of use the dual of that. So that very first step would be a non-starter if we wanted to go beyond exponentially tailed losses. So I'm not going to go into all the details of this because I don't have time, but I will just mention that the proof technique really relied on these explicit convex program characterizations for the SVM and for the minimum norm interpolation. And this is not something we can do more broadly. So what happens if we think about general losses that are neither exponentially tailed nor square? For that, we provide our main result, which is to show that something similar happens. The loss functions still do yield similar solutions under very high dimensional data, but we no longer have an exact result. What we now have is an approximate equivalence result. So this is what the result looks like more formally under the assumptions that I stated earlier on the loss function. And again, with high probability over the covariates, but for arbitrary labels. What we can do is we can look at a notion of directional error. Like we look at the limiting solution obtained by gradient descent and normalize it, and we subtract that off by theta mni divided by the norm of theta mni. Effectively, this is like the angle between the two solutions. That's kind of what the left-hand side of this equation corresponds to. We show that this notion of directional error is at most this quantity, which decays as the effective dimension of the model becomes larger and larger. So we have a max of root n over d2 and n over d infinity. So d2 and d infinity are what I defined already on the previous slide. And what this result is effectively saying is as n, and if we are in this ultra-high dimensional regime where d2 and d infinity grow superlinearly with n, we expect the right-hand side here to go to 0. And therefore, in this regime, and under our assumptions on the loss functions, all the loss functions become approximately equivalent when done with gradient descent under this kind of ultra-high dimensional regime. And a specific conclusion that will be useful for the later part of the talk is that we are basically saying that in all of these cases, the implicit bias is approximately very similar to this very simple solution of minimum norm interpolation. And what turns out to be nice when we want to do error analysis later on is that the MNI has a closed form expression of the form x, where x is the data matrix x pseudo inverse y. So that was the main result. If anyone has questions about the statement of the result, I can pause for a minute.
Maybe I have one. So here, basically, with respect to the result in the previous slide, this is just a generalization where you do any loss function under reasonability.
That's right. That's right. Yeah. Maybe.
Can you say again what are the assumptions on the loss function?
Oh, sure. So the loss. Okay, wait. Okay, so we assume that the loss function is convex. We need it to be twice differentiable, just for the proof techniques, strictly increasing, attaining a minimum at minus infinity. And there are like a couple of other assumptions made in the work of G and Telgarsky that I think are hard to explain in an intuitive way. Basically, it's something kind of like the limits of certain functionals like L prime of L inverse of Z divided by L prime of L inverse times AZ, like these limits kind of exist. And just some I think of them as regularity assumptions. They're a little hard to interpret, but they're pretty mild.
Thanks.
Yeah.
Someone else?
Okay, yeah, I can continue. all of this. Okay, so we have this general result. In terms of, I'll also comment that we are able to say something about necessary and sufficient conditions for the exact equivalence I presented for the exponentially tailed loss case. First off, we are able to recover that result. But more generally, we're able to show that if we don't have an exponentially tailed loss, the exact equivalence happens if and only if the label vector y is an exact eigenvector of the Gram matrix XX transpose. This is hard to interpret, I think, in any specific model. One sense in which this would happen is if the Gram matrix was exactly proportional to the identity, then a lot of the proofs do simplify in this nice way. But this is an if and only if. So we can show that in the absence of either of these, we only get an approximate equivalence. And I won't talk about this today, but a lot of the proof ideas seamlessly extend to the multi-class case, where some of the earlier proofs that used the SVM were actually more complicated. And I'll also talk about what happens with losses that are more per example, where you put different weights on different examples. Right now, the theory I presented so far assumes that all examples are treated equally, but we can modify the theory a bit to accommodate some of these cases, and I'll say more about that as we go along. I want to say a bit about the proof, and this is where I'm going to focus on proofs a little more. So the first step, in some sense, leans on this very beautiful work by G and Telgarsky, where what they essentially do is they interpret gradient descent run on this kind of general loss function in terms of a nice kind of mirror descent update, where what you do is you take the theta t's and you multiply on both sides by the data matrix X. And you sort of get this nice characterization where you have, this is called the primal, x theta t plus 1 is equal to x theta t minus some modified step size. So you do some different normalizations here. And then you have a Gram matrix. And this can be written as the gradient with respect to some potential function, which is like a generalized sum. So it's like L inverse of sum of L. This is, I think, a very non-trivial observation and very important for everything I'm going to say. But the sense in which this is mirror descent is because I'm sort of doing the update in the dual space given by the gradient of this generalized sum psi. So maybe I'll actually mention one other assumption that I did not talk about that is important for our framework, which is that this generalized sum does need to be convex. So from this, what you can sort of do is, it turns out that this dual variable, although this stuff is going to converge to infinity, the dual variable converges to something finite. And their main observation, so they also use this to get like faster convergence rates and things like that. But for the purpose of understanding the eventual solution, a very nice observation that they made was that essentially you can extract out the primal solution, at least in terms of the limiting direction, in a closed form way out of this dual solution. So that's the high level thing to take away, even if you didn't understand all of that. Basically, we can get the limiting solution as a closed form expression if we can solve for the dual. And the dual satisfies a certain quadratic objective that is X transpose, and there's a multiplication of the labels times Q. And this is an L2 norm squared optimization problem, subject to a very, I think, difficult to interpret constraint, which is like basically the convex conjugate of this Xi object. So this was our starting point. This is still difficult because this is a convex conjugate. This is, it's not closed form, but also it's, I think, not very intuitive. It's a little difficult to see what that constraint is really corresponding to. So our kind of first step was to provide an auxiliary convex program for the dual that turns out to preserve the optimal solution and is somewhat simpler to work with. So essentially what we did was we sort of relaxed this constraint into constraints involving the positivity of the dual variables qi and a constraint of the form 1 minus some g inverse qi is less than 0, where g is some sort of convex function. So again, you don't understand all the details here, but this is a lot, at least this is explicit and it's simpler to think about than some Fenchel conjugate thing. So this gave us a simplified convex program of this form. And some fun facts about the g function, which is usually a function of L, and we were able to show this is always convex. In the case of exponentially tailed losses, this is just the identity function, and in fact, Q turns out to correspond to the SVM dual. So some nice observations that we made along the way. So moving on, we've reduced our problem to studying what happens with this objective under random data. And Here I'll try to provide a little more intuition. So in very high dimensional regimes, as we've mentioned, fairly elementary random matrix theory tells us that we need that the Gram matrix will be pretty close to a multiple of the identity. So what happens if it's exactly the identity, right? Then this whole thing simplifies to just the L2 norm squared of the dual variables. And then we have these constraints, and at a high level, these constraints are symmetric. They're all like, they're treating the dual variables equivalently. So it's actually not difficult to see that in this case, the dual variables would all be the same. And in this idealized case, we will, plugging things back into our primal dual relationship, you get a very simple expression, which is just summing up all the training examples, x transpose y. And because xx transpose is the identity, you end up getting the theta mni from this. So that's kind of the idealized case. In the case where, this idealized case where the Gram matrix is the identity, you can actually solve this closed form in this very nice way. Of course, in the real world, we do not expect this exact equivalence, like things are only approximately the same. So we needed to do a kind of sensitivity analysis and get a similar type of conclusion, but now in just terms of the directional error. And at the right-hand side, we have the normalized error between the Gram matrix and an appropriate multiple of the identity. This was in some sense the most difficult part of the proof. I'm not really going to get into more details, but at a high level, we start with the KKT conditions and do a sensitivity analysis from there. One thing I will mention about this result is that this is completely fixed. I've not assumed any random data in this particular result. This is a fixed design result. So in principle, if you are able to understand the Gram matrix of your data in any setting, you could plug it in here and get a result. So we're not assuming explicit data models over here. Okay. Okay, so that was proof sketch finished. I'll now say a little bit about what happens in the OOD setting that we are interested in. Here our results are somewhat weaker, but we can still get some interesting insight. So now we have a training data set, and we have some labels that are designated as minority examples. So in particular, we have a minority group subset that is given by S, and this is typically a small subset of the set of training examples. And now the way in which we're going to deviate from the previous framework is we're going to have like per example loss functions. So our loss is going to be upweighted for all examples in the minority group. So we have this delta inverse term where delta is less than 1, so this is going to be greater than 1. And we consider the majority examples, everything else, and we do not weight those at all. So this is an importance weighted training loss, and this actually no longer fits in our framework because now we are doing these per example losses. However, for some idealized scenarios, we are able to get some interesting insights. Specifically, if we do this importance weighting with polynomial loss, and by polynomial loss, I'm just saying that L of the argument is going to decay polynomially instead of exponentially in the argument. We end up seeing that, and then under this idealized assumption of the Gram matrix, we get an equivalence to this notion of cost-sensitive interpolation. So I still have the pseudo-inverse of x here, as you expect from an interpolating method. But now my labels are adjusted, where if I'm in the majority group, that is if I'm not in S, the labels are preserved. But if I'm in the minority examples, I kind of upweight them by this delta to the -1 over m plus 2. So if the degree m is smaller, if the loss is more heavy-tailed, then this is going to be a stronger effect. And in the extreme case where m is going to infinity, which is like an exponential loss, this effect is going to completely drown out. So actually in that case, there will be the importance weighting effect will completely drown out as m goes to infinity. And this explains some nice observations that were made in this paper by Wang et al. I'm not going to go into too much detail on these figures, but roughly what they saw was that the decision boundary for no importance weighting and importance weighting remains the same in the case of the log loss. But for the case of polynomially tailed loss, they actually see this difference. So in some sense, this result kind of explains this type of observation. How am I doing on time? Yeah, I can do that. I might go a bit, I might be more high level for the next part of the talk, given how I'm doing on time so far. Okay. So high level takeaway from the first part of the talk, all loss functions reduce either to interpolation, like minimum norm interpolation, or the sense of cost-sensitive interpolation. What's nice is that these are simpler objects. They have closed form expressions, and that's nice for getting sharp analysis, and that's what we're going to do next. Here I won't do any proofs. I'll keep things at a higher level. So I'll start with in-distribution analysis, and this is actually older work, but I want to talk about it at a high level because just to illustrate the value of having these types of equivalences. So in the in-distribution case, some of our older work looked at an over-parameterized logistic model, and here I have a link function that encodes label noise. I'm going to make assumptions that make this friendly to linear models, namely that the expectation of z times g of z is greater than 0. This excludes a lot of the single index models that I think were talked about yesterday, but it is not bad from the point of view of linear model analysis. And I'm just recapping my assumptions on the covariates. Based on the previous part of the talk, I'll focus on the minimum norm interpolator. And our error metric is going to be the 0-1 error. That is the probability that the signs of the estimated model and the true model do not match. And our focus here is going to be on consistency, where this is why looking at the ultra-high-dimensional regime is valuable. We can actually drive the test error to 0 as n and d go to infinity. And the setting I'm going to study here is going to be one with anisotropy in the covariance matrix. This turns out to be necessary to get consistency. If you look at a lot of the work of Peter Bartlett and others on benign overfitting, you'll see these types of conditions are required. Here I'm specializing things to make the result more interpretable. And I just have a spiked covariance model where I have S top eigenvalues and D minus S bottom eigenvalues. This is parameterized by N and D, the number of spikes S. And in some sense, the most important parameter is the ratio, that is the magnitude of the top eigenvalue divided by the magnitude of the bottom eigenvalue. Intuitively, the higher the value of this ratio, the more favorable things are for generalization, both in regression and classification. I'm also going to assume that theta star lies entirely within the spike. All of this turns out to be necessary for benign overfitting. I'm happy to talk more about that offline. And I guess that's what I just said. The Gaussian mixture model turns out to satisfy this type of assumption. And this also arises, we expect this to arise in some sense from feature learning, which is reducing our effective dimension of data. OK, so our main result here basically showed a separation in consistency between regression and classification. And it used the sharp analysis of the MNI in this sense. So the work by Bartlett et al. From 2019-2020 basically showed that in specialized to the spike covariance model, if the ratio grows much faster than d over n, regression generalizes, and this condition is in fact tight. We showed a weaker condition that if the ratio could be less than d over n, but it still needs to exceed root d over n. And then regression does not generalize, but classification does. And we also, our results were tight. If the ratio was less than root d over n, then neither of the tasks would generalize. This was a very clean result that we were able to show in this generality. And this separation does not follow from generalization bounds in learning theory and things like that. It can be recovered from exact predictions. So there was this nice work by Montanari et al. On the error of max margin classifiers that also appeared around this time. And subsequently, they were actually able to recover these results as a consequence of their predictions. But that takes a lot more work than what we did. So I just wanted to mention that. So that's kind of taking away from that in the in-distribution case, we can use these equivalents to MNI to get, I think, relatively simpler analysis and get these discovery of these new phenomena. I don't know how much time I'll have for the out-of-distribution stuff, but we'll see. So in this case, we consider a Gaussian mixture model. And I add in this attribute for each data point, which indicates a majority group if the attribute matches the label, and a minority group if it does not. And I'm going to consider a Gaussian mixture model where I have a core feature given by mu c and a spurious feature given by mu s. And it's actually, in some sense, easiest to visualize this through a picture. So the majority groups here correspond to yi being equal to ai. So you have these big clusters. And then the minority groups are the ones that ai is not equal to yi, and you have these much smaller clusters. And this is motivated by many practical data sets. One example is the water birds data set, where yi denotes the type of bird, water or land, and the ai denotes the type of backgrounds. As you might expect, minority examples are ones where the bird and background do not match, and these are the difficult or minority examples. So in this setting, our goal is to study the cost-sensitive MNI. And in particular, we want to analyze the majority group error and the minority group error separately and get sharp non-asymptotic expressions matching upper and lower bounds up to multiplicative constants. So, okay, so depending on time, I'll see how much I can get through with this. We define these notions of total signal strength, the sum of the the L2 norms of the core feature and spurious feature. Remember, in Gaussian mixture models, these are very, you expect that you want these to be large, because this will mean the mixtures are more well separated. We also look at the difference, which is a useful quantity because it tells us in some sense how much larger the core feature is than the spurious feature. And again, ideally, we would want this to be large. Some assumptions on the regime, which I'm not going to get into due to lack of time. At a high level, we get we get non-asymptotic expressions that match up to constants. So the rate in terms of n and d is sharp. Not only in terms of n and d, it's sharp in terms of all of these factors, like the total signal strength and the signal strength difference, and also the number of majority and minority examples. Interestingly, although we studied interpolation, you get identical rates in terms of all of these quantities, even if you do explicit regularization. So we can specialize this a bit. And a particularly interesting case in practice is if the signal strength difference is equal to 0. And in this case, the expressions simplify a bit. And I won't go through all the math, but I'll just say qualitatively. To reduce the worst group error, what we need to do in some sense is increase the importance weight effectively, or decrease delta minus on the minority example, increase the total signal strength, as you might expect. And the last one, I think, is the most interesting. We want to increase the number of minority examples. So our result actually says that you would not get much benefit from increasing the number of majority examples. You need to increase the number of minority examples. And then maybe I don't have time to talk about this, actually. I can talk about it if anyone has questions. But at a very high level, what we could show through this is that there is a interesting trade-off between robustness and accuracy, depending on how you set the weights, the delta plus and delta minus. We believe this trade-off is fundamental information theoretically, like you actually need more minority examples to do well on minority data. And we're working on formalizing this. That would be an interesting result because the spurious correlation model is actually pretty stylized. It's not obvious one way or another how this would go. Okay, so I'm gonna end over there. I'll just leave you with a couple of high-level takeaways. In the in-distribution case, we saw that general losses yield very similar solutions. The equivalence to MNI simplifies error analysis. And in the case of out-of-distribution, we got this equivalence to a cost-sensitive MNI, and this gives us some tractable analysis over there as well. I have thoughts on what you can do beyond linear models, but maybe I'll leave that for questions if people have any. So I'll thank you all for listening, and I'm happy to take questions.
Thank you for the very nice talk. Questions?
Okay, you were asking for it, so can you comment a bit more on the spurious correlation part? So
sure.
Beyond just increasing the minority group, what else can you say with your analysis?
Sure. So let me actually, maybe I will talk about this slide. So, or maybe I'll go back to this case. So I like specializing the result to this kind of case where the signal strength difference is 0. What this means is that the magnitude of the core and spurious feature are identical. This is a hard case. This is an interesting and hard case because, in some sense, the data is going to be quite reliant on the spurious feature. So here what we see, and maybe focusing on the case of minority group error, is we see that this is going to decay with the number of minority examples n minus. It's going to decay with the total signal strength. Both of these are sort of expected. And it's going to also decay with alpha minus, which turns out to, this function is going to increase if we decrease delta minus. So if we upweight the minority examples, then this would increase as well. And the whole error expression is also going to be worse if d is increasing. So there is a cursive dimension, data dimensionality in this result. What's nice about this result is you can actually plug in various choices of delta plus and delta minus and observe trade-offs. And that's what I didn't have time to talk about, so I'll quickly mention that. So maybe the figures here show the plot of test error as a function of the total signal strength. this one is in the case of what I call proportional weighting. So I'm setting my delta plus and minus proportional to the fraction of my majority and minority examples. If I have access to group labels, I can do this. And here you see that both errors kind of decay at a very similar rate. This turns out to actually be the case. And in both of these cases, we have conditions on the total signal strength that need to be satisfied for consistency. On the other hand, if you did not do any weighting, then you see that the majority group error goes much faster. It goes to 0 much faster. But the minority group error is decaying at a much slower rate. And yeah, so that's maybe one other thing I would say. I think the biggest takeaway in some sense is that the rates, so from the point of view of the minority group error, which is the orange curve here, either you do no weighting and your rate is actually pretty terrible, like you need the thing to go as d times n divided by n minus squared. If n minus squared is a constant, then this becomes d times n, which is quite stringent. Or if you have proportional weighting, you get a better rate, but even then, you actually need your number of minority examples to be sufficiently large. And this is something like, it's unclear a priori whether we would have expected that. I actually started this whole project thinking that maybe the number of majority groups could change the bias in some way and make things better.
Okay, so maybe very quick. Do you think this is robust if you take a nonlinear model?
That's a great question. I think with the nonlinear. So from the point of view of the nonlinear model, I think the question I'm most interested in is how does a nonlinear model learn representations of this type in the first place? There's some evidence that, like for example, there's the simplicity bias in neural networks, and there's evidence that maybe neural networks tend to learn these shortcut spurious features. I think from the nonlinear point of view, I would be most interested in understanding how we get to models of this type, because there's also empirical work showing that these types of Gaussian mixture models actually do arise at the last layer of a neural network, for example. So I would be most interested in understanding that mechanism.
Any more questions?
Hello, thank you for nice talk. Your loss function is actually convex.
Yes.
Okay. So what is about the practical validity of this assumption, like convexity of the loss function? So my question is about the gap between the theory and practice when we are considering the convex loss functions. And I would also like to add another question. What will your approach to reach the minimum when the loss function is convex?
Okay. I think to answer that, I'll maybe go to what I was going to say from the linear to the nonlinear work. This is a bunch of speculation here. So first of all, when we talk about a convex loss function, there are two elements to it. Like one is the loss function L convex in its argument? So like, if you take a nonlinear model and you're going to replace yi times xi transpose theta with like yi times f theta of xi. So the loss function is still typically convex in its argument. I don't think I think in practice, loss functions satisfy this assumption. What will change is that the loss function will no longer be convex in theta, because now you have neural networks and things like that. Definitely the current theory relies on convexity of the loss in its argument on theta quite a bit. And the reason is because we are using implicit bias theory as a starting point, the fact that we converge to a global minimum and that we get something. There are some variants in implicit bias theory for neural networks. They're just kind of weaker. There are nice results by Liu and Li, like for example, showing that you get to KKT points of margin maximization and things like that. I think one thing I'm hopeful about is that some of the tools that we use could potentially be used to understand what happens with those KKT points a little better. It's challenging because the KKT points are conditional on reaching a global, like that characterization is conditional on reaching a global minimum. So there are lots of challenges, I would say, when you go to neural networks that remain open. This is very speculative, but I'm hopeful that random data can help us. Even just random covariates, not even necessarily assuming a full signal model, but even assuming random covariates could tell us something about those cases. So I'm currently working on this.
So in the interest of time, we'll conclude this talk here and defer further question to the break afterwards. Thanks. Thank you, Vidya. Very nice talk. All right.